Professor.
Yeah.
So many thanks for accepting our interview. As a well-established scholar who had so many outstanding achievements in field of both mathematics and physics. So your research work on Snowd theory, deformation, causation, mirror symmetry has profoundly influenced modern mathematics. So in today's conversation, we hope to delve deep into your field of research and also your cross-cultural academic experience.
Okay.
So the first question is about your research work. You are a world-renowned mathematician, but your research work is also closely related to physics. So based on your experience, what do you think the link between mathematics and physics, and how do the ideas from these two disciplines inspire and promote each other?
Now there are many deep relations, and of course even many centuries ago, development of mathematics, physics influenced each other. Like main equations in analysis come from physics. It's like heat equation or wave equation, or this laws of Newton. Relations are always like this. But I was interested in there is a classical mechanics which became part of mathematics in terms of like symplectic geometry. But then there was quantum mechanics in the beginning of the 20th century, and then quantum field theory, and eventually a bit more, it's very abstract and maybe not related to our world, string theory, which is next development, and they have their own, and also the statistical physics, and there are very deep, many relations with various structures in mathematics. Like quantum mechanics, it's replacement of commutative world by non-commutative world, and it's very deeply related to algebra, and but also operator theory and functional analysis. And in quantum field theory, it's another amazing, from mathematician theory, it's some kind of theory of infinite dimensional integrals, and we're still struggling to make sense of these infinite dimensional integrals, but also it's because infinite dimensional, it's one think it's a glimpse of some infinite dimensional geometry. So we use usual finite dimensional manifolds to get finitely many parameters to describe the system, and this is a well-defined kind of field of geometry of manifolds or differential geometry. But in infinite dimensions, things are much more mysterious, and in physics, give at least some way in some situation to see things in somewhere in half infinite dimension, or some kind of very interesting story. But also this quantum field theory, it's not arbitrary infinite dimensional integrals. They are organized by principles of locality. Actually, it was absolutely amazing discovery, of really formal discovery in the 60s. People realized that notion of statistical physics with local interaction, like boiling water, and quantum field theory are formally very similar, and through complex analysis, if one go from a real time to imaginary time, one goes from statistical physics to quantum field theory. It's absolutely amazing formal discovery, but the structure of two completely different domains of physics, mathematical structure, is on formal level similar. Analytic, it's very different. You got oscillating integrals and kind of like fast decaying in quantum physics and fast decaying integrals in statistical physics, but formal story is the same. And this notion of locality gives notion of was related to theory of cobordisms, and there are some specific situations called you get topological field theory, get topological invariance, which became recently very prominent in topological states of matter. So one have kind of amazing materials which behave with superconductivity properties, and it's deeply related to algebra, but different algebra from what quantum mechanics starts. It's also sometimes somewhat relates called quantum algebra, but also some category theories. And for example, there was like thinking about topological field theories, people formulated some question called cobordism hypothesis, and turns out it's deeply related to fundamental questions of topology of manifolds and category theory. Yeah, so the relation is really multitude. In static physics, it's very, many objects got many ideas, and we can formalize some small parts of it. And physicists also very happy when we can formalize some parts of it, because it gives some kind of very solid calculational tool. So yeah, so the interaction goes very closely one way to another. And during my career, I have experienced many fruitful interactions in both directions. So, for example, I'm the only mathematician who got breakthrough prize in physics. Yeah. So I was adopted because it's really many things which I discovered. I learned something from physics, but physicists also learned from.
Yeah, I think statistic physics is a good example for the deep relation of mathematics and physics.
Yes.
So we come to the next question.
Yeah.
So you have made many important contributions in geometry, deformation theory, and topology. So how do you think these findings will impact the future mathematical developments, especially in emerging fields?
I don't know what in emerging fields in mathematics. No, definitely it's changed enormously our understanding what is important in mathematics. There are really new structures became, which almost unnoticed before, became central. And mathematics is really deeply it's evolving subject, and interaction with physics plays absolutely fundamental role in kind of finding new questions and new area of interest. And I think it will continue. Answering your previous question, I didn't talk much about string theory, but the string theory, it's related. I think it has enormous potential to have interaction with mathematics. What was most visible, like 30 years ago, it was interaction with algebraic geometry. In string theory, you have strings which evolve in time, get surfaces, and surfaces are complex curves, algebraic curves. So it was related to theory of algebraic curves, and there are many absolutely amazing ideas coming to algebraic geometry coming from string theory, and also participate in interaction with category theory, some other category theory related with homological mirror symmetry. A dialogue with physics was absolutely indispensable in this story. But there are so new structures which definitely we see that should be understood in the future.
Last time Professor Lahon, you know him?
Lafort.
He used the geometry method to do the mathematical work. Maybe can do many useful work on artificial intelligence technology.
Could be. My work definitely not related to this direction, but there was some research which was involved last 10 years. It's notion of resurgence. It's about kind of new class of analytic functions and kind of infinite behavior, which you can see functions of few variables. And this is related to maybe even to very not to quantum field theory, but even quantum mechanics. And it seems that this new picture which I developed with my co-authors will give very efficient algorithms to do calculation and analysis. It's super high precision calculation, doing it kind of very fast. But we have, it comes from all understandings of all many areas together. We have very unified picture which applied even to such well understood story as quantum mechanics, and it could be useful to even to calculation of potential. It's good to calculation to some spectra of like molecules, and kind of real life quantum physics. It has a good potential to be useful.
So, in addition to geometry, many branches of mathematics has made an important impact on natural science and engineering developments. So, such like optimization theory, matrix theory, and statistics, and queen theory, and in addition to these well-known fields, what other branches do you think will have an impact on future
of course, it's,
progress
the
of
obvious
science?
example is number theory. Long time ago, 100 years ago, there was a British mathematician Hardy. He wrote a book, Apology of Mathematician, and he wrote that presumably number theory will be most useless part of mathematics, and he's completely wrong. Because it's in coding theory, it allows to make amazing algorithms, very fast algorithms, which are used everywhere.
So, what other branches of mathematics will impact the future science and technology's
it's
progress?
hard to say, because what you mentioned is kind of these domains of mathematics are kind of have special flavors. They are like optimizations. There's some kind of real numbers. You make something optimal, and it's not always in mathematics. Not do it. But just philosophically, real numbers is very interesting field. But it's more important for mathematics. Complex numbers, which but for pure mathematical point of view, complex numbers are more fundamental, but they have their own intuition in doing complex numbers. Of course, real numbers appear as something like a measure of when you do something. You want really, in all mathematics, you want to estimate size. The sizes are real numbers, but there is kind of completely different direction when you look in complex world, and quantum mechanics says we have actually complex numbers behind everything, not real numbers. That's kind of like two different like halves of mathematics. One that's kind of attached to real world, and another to kind of more to inner beauty and this more relation to algebra and. Of course, these things interact very much with each other. And in my work, of course, I do things in both directions. But for me, like real numbers are like a way to measure things but real interest in complex numbers. So at the moment, I don't see much of potential use for my mathematics in this, but I get to have a great respect to this part of mathematics.
I think so.
But eventually, I think something will be useful. Of course, most part of mathematics is not useful. Kind of 90. But what is useful is extremely useful.
Because Chinese 无用之用. It looks no use, but it's useful from the long history perspective. So it's similar with your philosophy. So let's talk about your cross-cultural academic experience. So we know you have worked in several famous research institutions in Moscow, in Germany, in the United States, and now in France. So, we are curious about the unique characteristics of each of these first-class research. So, from your perspective, could you tell us some about that?
It was, for example, in Moscow, I was in Institute for Problem of Information Transmission. It was a very long time ago. It was before Perestroika. It was between 80 and 85. Yeah, it was kind of sufficiently short period, but actually I really liked this time. I was given almost complete freedom. Yeah, and people saw that I good in mathematics and proposed me this position, and but I was exposed. But I was really grateful to this period because I was exposed to questions that in kind of statistical physics, say, and in coding theory, and many questions, and already at that time it gave me idea of topological field theory. Yeah, idea of locality I learned from this from chief of my laboratory, who was a great person in statistical physics, and he invented kind of right notion of locality in statistical physics, and I got the idea from this period.
So actually our last question is about, could you please tell us someone or something who made an important impact on your research work and your career developments, and you mentioned, so
many people. I had a great teacher in Moscow. He's one of the greatest mathematicians of 20th century, Israel Gelfand. Not essentially directly from him, but from his seminar. He was seminar every week on Monday. It was seminar which lasted something like 4 or 5 hours in the evening. Yeah, very, very late, maybe from 7 o'clock till 11. Yeah, sometimes even later. And it was open to all mathematics, and one have kind of completely new speakers and discuss new topics. Yeah, it was a really great experience, but also in Moscow I learned from other great mathematicians, Manin and Arnold and Novikov, and so there are many, really many great mathematicians. And in physics I have to mention Edward Witten, who's the only physicist who got Fields Medal in mathematics. He is really genius, and he invented for the relation between mathematics and physics. He contributed really in a fantastic way, and so I remember when I was in Moscow, I learned his preprint, when he appeared every few months, and it was really good development. Yeah.
Actually, you won the Fields Medal about 25 years ago.
Yeah.
And after that, actually, you have made many different significant achievements. So I'm curious, what's the motivation on your long journey in mathematics research?
I have kind of always I have many projects which are unfinished, and lasting maybe like 30 years, some years, 30, 40 years, and always curious to study this. And actually I think I made many conjectures in mathematics, kind of maybe too many, but mostly correct, I have to say. So it was my way to contribute to mathematics, not only to prove theorems, but propose the right formulations, conjectures, which was very important.
So as far as I know, apart from mathematics and physics, you also have strong interest in the field of computer science. Yeah.
It's a kind of practical interest. Not. I don't really.
The computer science.
Computers. Because I used to do computer experiments in mathematics from quite early age, and I remember even back in Moscow. When I was in kind of like mid-80s, my father went to a conference in Western Europe and brought a small computer. It was 64 kilobyte memory. It was one of early. It was essentially a keyboard which has a little plate. And he bought it for $10. It was like this. It was without any documentation, And then my brother, who was actually had a serious education in computer science and electronics, he looks, okay, here's outputs, okay, he measures voltage, and then connected with TV sets, and then after a few minutes we saw the screen, and then we were able to make a little some programming in basics, and so it was quite fun. When I was a kid, so we played with this one of first personal computers, and already at that time I made some computer experiments, numerical experiments, and then which.
Okay, actually it's age of artificial intelligence. Don't you think artificial intelligence will change the method of mathematical research?
I never was involved with artificial intelligence, but I talked to people and roughly understand what is going on. And in spring there was a meeting here, exactly here, at Lagrange Center, and there were some people doing neural networks and interested in mathematics. They have learned this neural network to solve planimetry problems very better than average gold medalist. Like this. But it's no. This is not really surprising. But I suggested them some class of problems which I kind of encountered already like 30 years ago, and so they're very hard to. You have some very natural systems of linear equations, very determinant. You get much more equations than variables. That's a billion of equations and 100 million variables, something like this. But it's grows. It depends on parameters. Grows very fast, and very fast. You don't have cannot even write the solution because there's not enough memory. Even if it's modern computers, it will be never enough memory because it's very soon became the size of universe and things like this. But in principle, it's possible that artificial intelligence can help us to at least guess solutions, to make the right guesses. It's not to prove something, but at least make experimental work with these normal structures, which are very, really important in mathematics.
But currently, I think most of scientists have to pay attention to artificial intelligence technology. Is that true? It's
no, of course. When you do some kind of like biology, physics, or kind of experimental physics, when you get some models, it's definitely indispensable. But in mathematics, it's not yet the story. Because most part of the structures in mathematics is almost unapproachable by computer.
So could you tell us some of your personal interests in your life?
Actually, I like to listen music, but also I like biking, for example, and I kind of really want travel and not travel, but nature, and this is my. When I have free time, usually I go to walk or biking. That's my.
Okay. So you bike every day?
If it's not raining, I try to go almost every day.
Do you think this personally interesting have impact on your mathematical research or your personality?
No. I think it's kind of, for me, it's way too not to think.
Oh, no.
No. Of course, it will be dangerous. No, when I'm biking, I'm definitely not thinking about mathematics. It will be otherwise too dangerous. No.
Okay.
No. It's kind of like go to some perpendicular activity.
I interviewed with a mathematician, and he likes hiking
Hiking,
And,
yeah.
hiking. He told me. So I asked him why you like hiking. So he told me, so you listen to the sound of mountain when you hike.
Yeah, sure, yeah.
So he said it's similar to you listen to the sound of mathematics.
Yes, yeah. It's kind of spiritual. It's very similar. But it's a different part of the brain. But in
similar.
sense, it's similar, yeah. And also, I don't know. For example, it's also now kind of a bit fascinated. You know, those like people cannot fly, not birds, but now there are drones, and one can kind of like almost fly. Yeah, it's kind of really amazing experience. Yeah, which is
okay. Yeah. Could you please recommend some books you like to the young?
I have to say that I read not much these days. Yeah, I like to read about history and
history.
Yeah.
I know many mathematicians like to reading history.
Yeah.
Why?
Yeah. No. Kind of. I don't know. I want to feel kind of related with people from the past. Yeah, kind of like to see mathematics, kind of mankind on a large scale. Yeah. So definitely. We are not so different from people 2,000 years ago.
Okay. Yeah. I think so. Yeah. Okay. That's all the questions today's conversation.
Yeah.
Thank you so much. I know you have a very busy schedule, so thanks for your take time out of the schedule and shared with us your insights and your opinions.
Yeah.
Thank you so much.
Oh, thank you.